Hello everyone, my name is Minuk Ma. I'm going to talk about our Bootcamp Lecture 1. The topic is MDPs and exact solution methods. There are some reinforcement learning success stories, but let me skip this. So let me talk about Markov decision process before we move on to the details. MDP is defined by 7 factors: the set of states S, set of actions A, transition function P, reward function R, start state S0, discount factor gamma, and the horizon H. Actually, depending on the book, MDP is defined by 5 factors and 6 factors sometimes. As depicted in the figure, the agent gets state ST at every time step and decide action AT, and it gives it to the environment. Then the environment returns 2 things, the reward and the next state. The goal of MDP is to maximize this quantity, the expectation of cumulative discounted reward. In a simple word, it's just maximizing the total reward, and we want to find the policy pi, which maximizes this quantity. And in the right figure, the set of states S is the coordinates, and set of actions is east, west, north, and the south. The transition function exists, and the reward function is +1 at here and -1 at here. The start state is here, and the discount factor gamma is going to be about 0.95 or 0.99, something like that. And the horizon H is going to be either infinity or a very large finite number. So in this lecture, we're going to talk about value iteration and policy iteration. For now, we're only going to think about small discrete action state spaces, as they are simpler to get the main concepts across. We'll consider large and continuous spaces later. Before we move on to the details, let me explain some of the definitions which are so important that they are going to be referred over and over again in the later lectures. So the first concept is value function. It's the estimation of how good the current state is. So given state S, the value function v pi s is defined like this, namely the expectation of cumulative discounted reward given current policy pi. And I said that the whole point of MDP is to find the optimal policy which maximizes this quantity. So the ideal value function is called the optimal value function, which is the value function obtained by the optimal policy. So we're going to find the policy which maximizes this quantity. And the third concept is called the action value function, or Q function. It's the estimation of how good the state and action pair is. So Q function is now a function of 2 quantities, state and action, and is defined in a similar way, but as I said, is a function of S and A given the current policy pi. Let me explain about Bellman equation. So the quantities I just explained, the value function, optimal value function, or Q function, they have a beautiful correlation which is described by Bellman equation. There are 2 types of Bellman equation: the Bellman expectation equation and Bellman optimality equation. Bellman expectation equation looks like this. For value function, given state S, basically Bellman expectation equation is the correlation between the value function at state S and the value function at state S prime. So at current state S, the value function is calculated by the reward function plus the value function at the next state, but we don't know what the value function, what state we're going to be. It's determined by the transition probability P. So R plus discount factor gamma and this factor, and the total transition is governed by the current policy pi, so we're going to take the expectation over action. In the case of Bellman optimality equation, rather than taking the expectation, we're going to find the maximum value over action. And in the case of Q function, it's defined in a similar way. And if there is a naive algorithm to calculate the values, the time complexity is going to be at least mn squared, when m denotes the number of actions and n for the number of states. Why is it? First of all, we're going to calculate the value function for all states, so n here, and we're going to take the expectation over actions, so m, and we also have to take the expectation here over s prime, so n, so m n squared. For Q function, there's one more a here, so it's m squared n squared. Let me explain value iteration. Value iteration is an iterative algorithm to calculate the optimal value function and the byproduct, the optimal policy. The algorithm runs in this way. We start from zero initialization for all value functions for all states. Actually, we don't have to initialize the value function in this way. We can use arbitrary initialization scheme, and the algorithm is guaranteed to converge. But for convenience, and there's for loop over the horizon for all states s and s. We're going to update our value function according to Bellman optimality equation for all states. And if we do this over and over again, it's guaranteed to converge. And after it converges, we stop the algorithm and decide the policy as the greedy policy. So let's look at how value iteration is implemented in grid world. So if you run value iteration in the simple grid world setting that I explained before, at first, at zero iteration, all the value functions are initialized as 0. And at first, after one iteration, the goal state is 1, and the whole has -1. And after this, the values are started to be updated. But one observation is that value functions are updated from the goal state and propagates to the other states. Although we calculate the value functions for other states like here, according to Bellman optimality equation, the neighboring value functions are 0, so basically it's not updated. The value function is updated only when not all neighboring states is 0. So this is pseudocode for value iteration. Basically, it's just the same value iteration algorithm that I explained before. Initialize value function as 0 for all state s, and we increase the horizon and calculate the value function for all states according to Bellman optimality equation. And it'll give you a list of value functions and a list of policies. And we do this algorithm before it converges. So this is the core part of value iteration, the code. So check the arguments. It gets MDP, the discount factor gamma, number of iteration, and there are 4 for loops, 1, 2, 3, 4. So one is the loop for the horizon. The second loop is for the state, because we want to calculate the value function for all states. And the third loop is about the action, because we want to maximize this quantity over action. And this sigma is here, and the transition probability also is related to one for loop. Before I explain some demo, let me explain the environment that a value function is applied. It's a simple 4x4 grid world where S denotes the starting point, it's safe, and F denote frozen surface, which is also safe. But H means hole. It's not safe. You fall to your doom, and the game is over. And G denotes the goal state, where the frisbee is located. So the agent has to reach the goal state without falling into the hole. The agent receives a reward of 1 if it reaches the goal, and 0 otherwise. So we are going to estimate the value functions of each state. As I explained before, just like in the grid world, it operates like this. Starting from the goal state, the value functions start to propagate throughout all states. In this problem, the reward is sparse because the agent gets +1 of reward only when it reaches the goal state, otherwise it gets 0. In fact, designing reward function that reflects the goal of the task well is crucial for success. So for example, what about we design another reward function? What if the agent gets +1 at 1, 3 here and +2 reward at the goal state? In this case, the agent still gets the highest reward when it reaches the goal state. But it turns out that it may fluctuate between 1, 3 and 1, 2, like this, to get the infinite reward, because the horizon is infinite. Value iteration is appropriate for small state and action spaces, as I said, and in practice, we have to stop the algorithm at some point when it converges. So let me explain the effect of reward design. As I said, what if we think about another reward function? It turns out that it doesn't work. In state A here, where the agent can get +1, but by fluctuating between this F state and A state, the agent can get infinite reward. Because going down incurs 2 holes at the neighbor, so it won't go down. The agent rather prefers fluctuating between F and A. Therefore, making the goal state have the biggest reward is not sufficient. There can be loops like this. So delicate reward design is required. Then how can we design a good reward function that reflects the goal state, the goal of the task well? Or how can we make the agent learn well in the sparse reward environments? These are some interesting questions to think about. And let me explain the effect of the discount factor gamma. When we actually all know that discount factor should be in between 0 and 1, but what if gamma has other values other than that? So when discount factor is negative 0.99, doesn't work. 0.01 virtually doesn't work. When it's 0.5, it sort of works, but the convergence speed is too slow. When it's 0.95, which is familiar to us, it works well. When it's 1, exactly 1, it does not work. So please set gamma as a real number between 0 and 1, but which is close to 1, but which is not exactly 1. This slide is about the effect of value initialization. So far, we have initialized value function with zeros for all states. But actually, proper initialization can boost up the convergence speed. After 8 iterations, zero initialization scheme have little convergence. But we have prior knowledge that after convergence, the optimal value functions is going to be higher near the goal state and lower near the holes. So if we initialize the value function in the increasing order, from the start state to the goal state, even after 8 iterations, it converges. We can check that the policy is optimal already. But if we initialize the value functions in the opposite way, we can see that after 8 iterations, the policy is not good. So the question is, how can we reflect our prior knowledge or inductive bias as policy initialization for deep RL? It's an interesting question to think about. Now let me give some explanations on the convergence of value iteration. Many technical questions can be asked. How do we know that value iteration converges, or that iterative policy evaluation converges, and therefore policy iteration converges? Is the solution unique? How fast do these algorithms converge? These questions can be resolved by contraction mapping theorem. Before I explain the theorem, let me define the infinity norm. We will measure distance between state value functions u and v by the infinity norm, namely the largest distance between state values. Think about a space whose element is state value functions. And we can think about a distance between one state value function and another state value function. And the infinity norm is the maximum distance between them. One important fact is that Bellman expectation backup is a contraction mapping. Let's define the Bellman expectation backup operator T-pi as follows, which was derived from Bellman expectation equation. This operator is a gamma contraction, namely, it makes value functions get closer by at least factor of gamma. So when there are two arbitrary value functions u and v, after taking the operation t, then the distance between two is going to be closer at least factor of gamma. So what if we do this operation over and over again? Then the distance between arbitrary two value functions is going to be closer and closer, and finally they will converge to one certain fixed point. Similar argument holds for the Bellman optimality operator as well. This leads to contraction mapping theorem. For any metric space V that is closed under an operator TV, where T is a gamma contraction, then T converges to a unique fixed point at a linear convergence rate of gamma. The Bellman optimality operator T star has a unique fixed point. V star is a fixed point of T star by Bellman optimality equation. And by contraction mapping theorem, value iteration converges on V star.
Here is a policy iteration algorithm. It includes two steps. The first step is evaluating value of state given policy. The value of each step is computed by take expectation of total discounted reward from time step t. The second step is policy improvement. We will find the best action according to one step look ahead. In other words, we will compute value given state and action, then choose the action with maximum value. In the first step, this equation can be solved by using linear system of equation or policy evaluation similar to value iterative method. The two steps are repeated until the policy convergence. In the policy evaluation, the policy can be estimated by solving linear system equation. This method applies for small NDP, and we need to know all the information of environment, such as the transition probability and reward during transition. The other method is iterative policy evaluation. Here is a pseudocode of iterative algorithm. It is similar to value iteration. We will update value of each state given policy in each step here. And we can stop early algorithm when the change of value of each state less than a small positive number. In the policy improvement step, beyond given evaluated value, we will compute the new state action value and then get the new optimal policy by find maximum state value action. We would like to know whether or not new policy is actually better than previous policy. As we saw, that step will improve the value from any state over one step. So that following below equation, it really improves the value function. Here is a policy iteration per pseudocode. The first, we will randomly initialize value function and policy over all steps. Secondly, we will repeat the following two steps until stop condition is met. In the policy evaluation step, we use the iterative policy evaluation. The input of the algorithm is the previous policy and the previous value. The algorithm will return the evaluated value given policy. In the policy improvement step, we will improve policy by find the best action beyond the action state value. The algorithm will terminate when there are no change in the optimal policy. Here is the implement code of the policy iteration to solve the frozen lake problem. Here's the policy iteration function, and here is the loop to iterate policy update. In each iteration, two-step policy evaluation and policy improvement are performed. In this example, we demonstrate policy evaluation by using iterative algorithm. In iterative policy evaluation function, the value of all states are computed iteratively. Here, this for loop corresponds to loop overall next state. Yeah. And this P is corresponding to probability transition state. And here is a previous value. In the policy improvement step, firstly, we compute state action value of all states. In this function, this for loop is equivalent to loop over next state. Then each state, we will take one action over 4 actions corresponding to maximum Q value of this state. Here is the result we will implement. And as you can see, the policy iteration can converge after 4 iterations. It's faster than the value iteration. And here is a policy iteration conversion guarantee. Since a finite MDP had a finite number of the policy, so that in every step the policy is improved, then given policy can be encountered almost once if it is not optimal point. After we iterated through different policies, we must be done and conversion. Yeah, I complete my presentation. Thank you.